Thanks very much. Over to you.
Thank you. Hi. Thanks so much for coming and for having me. And when Ben and Carol invited me, I immediately said I feel like an imposter because I don't know Python. I'm just learning R. I don't know any of these things we're going to learn about today. So if you also don't know this stuff, you're not the only one. And I said, I'd be happy to come and give kind of what I call the hearts and minds talk, which is I spend a lot of time thinking and writing about why we should do more transparent and open science and how we can make science more credible. So I'm kind of working more at the higher level thing rather than the technical side. I can't even figure out how to update my website to get my rank right so that you can get a sense of my lack of technological sophistication. So what I'm going to talk about today is kind of the bigger picture, taking a step back from my perspective as a journal editor, as somebody in the field of social psychology, which is kind of in the eye of the storm of the replicability crisis, and someone who teaches research methods. So my main core teaching responsibilities are to teach undergraduates about the scientific process, how we do science, specifically to psych majors, but really it applies at least to all social sciences and I think beyond that. So when I teach research methods to undergrads, one of the things I tell them is that scientists, really prioritize self-correction. That's one of the things that makes science different from other ways of knowing. We spend the first couple of weeks on the demarcation problem, what makes science different from, authority or intuition or other sources of knowledge. For years and years, I just taught them, of course, we prioritize self-correction. Of course, we want to know if we're wrong. We try to prove ourselves wrong. That's one of the distinguishing features of science. And then the replicability crisis hit my field, and I started thinking, are those just words? Like, what is the proof? What can I point to show that we prioritize self-correction, that we want to know if we're wrong? And this was captured pretty well in a tweet by James Heathers. You might know him as the guy behind the Just Says in Mice Twitter account. I don't know if you've seen that one, but it's a brilliant thing he developed. Anyway, he tweeted, "Science is self-correcting, sure, when we correct it, not because of magical progress." And I think this really drives home to me that we can't just go around saying science is self-correcting. We actually have to correct it, and we have to reward and incentivize correction. And that made me think about, well, okay, I'm teaching my undergrads about the ideal of what science should be like, and how would we design a system if we really wanted to prioritize self-correction? What would that look like? How would we design science? And in thinking about this, I learned about Robert Merton's norms of science. He was a sociologist of science working in the 1940s. And he published a set of norms. I think he was arguing more that this describes what scientists actually do. That's not my experience, but I think it's a useful set of norms to maybe aspire to think about what should we as scientists prioritize, what should our values be. So the four that he identified, I'm going to mention briefly here. The first is universalism, and this is the idea that the validity of a scientific claim doesn't depend on who's making it. It doesn't depend on how famous they are, on what institution they're at, what career stage they're at, and so on. Hierarchy shouldn't matter, status shouldn't matter. Now, of course, scientists are humans and we work in social and political systems. Hierarchy does matter, status does matter. But what we're arguing here is that in the moment when you're evaluating the validity of a scientific claim, those things should not matter. Right? That narrow job of evaluating, is this claim valid or not, or how valid is it, then it shouldn't matter who's making it. So this is really important and speaks to me as a journal editor. I try to blind myself to the author's identities for as long as I can. So when I first read a manuscript, I literally put my hand up to my screen so I don't see who the authors are, and I decide whether or not it passes the initial stage of review without knowing who the authors are or what institution they're at. And I've been trying to encourage other journal editors to do the same. And you can see why this would be important for a self-correcting system, right? If the highest status person or people at the most prestigious institution are making mistakes, we need to be able to catch that and correct it. And without this principle, that might not happen, right? If there's a hierarchy, if it's impossible for an undergraduate or someone at a lower prestige institution to challenge more famous people, then it's going to be hard to correct those errors. The second norm used to be called communism. Now it goes by communality. And this is the closest to the core values of open science. This is the idea that the findings of science belong to everyone. They're not private property. Open communication is key, no secrecy. This is debatable. Not everybody agrees with this norm. There's a lot of science that happens in industry, for example, where there is a lot of secrecy. And even arguably within academia, there's a lot of secrecy. But you could see how this would be important for self-correction, right? If we want to make sure we prioritize catching errors and and fixing them, then everything should be out in the open so that we have a better chance of catching the errors and fixing them. The third norm is disinterestedness, which is the idea that scientists should be focused on getting it right, not on their own success, and that we should report whatever we find, even if it makes us look bad. Again, there's controversy around this. Some people argue that individual scientists don't need to be disinterested, but the system needs to incentivize disinterestedness so that you could have adversarial theories or findings, and the goal of the community is to get at the truth, even if no individual scientist necessarily has that goal. But again, the larger principle here is that it's okay to criticize and to point out a flaw in something, even if it's going to harm someone else's or your own self-interest. That if I point out that this theory actually isn't well supported, and that means that person loses some of their speaking fees or notoriety or things like that, that's okay. That's more important to get it right than to protect scientists' self-interest. And you can see why that would be important for self-correction. And then the last is organized skepticism, which is the idea that we don't take things at face value. We expect people to verify our claims. We want to verify others' claims. And this applies even for claims that we would love it if they were true, that have political implications or societal implications. That would be great. It's still okay to criticize those claims and to ask to verify those claims. And again, you can see why this would be important for self-correction, that nothing is above verification and scrutiny. So how well do we do living up to these ideals? There's some research by Anderson et al. From 2007 where they surveyed scientists. These were people who had been awarded NIH grants, and asked them, they described these norms in plain language and asked them, do you subscribe to these norms? Do you act in accordance with these norms? And do you think other scientists you know act in accordance with these norms? So the top two bars are the mid-career and early career scientists' answers to, do you subscribe to these norms? The large proportion, the gray part, said yes. The black part are people who subscribe to the counter norms, so secrecy, status, etc. The next two bars are, do you behave in accordance with the norms? And already we see a value-behavior gap, right? People subscribe to the norms more than they say they behave in accordance with them. And then the third set of bars is, do you think other scientists behave in accordance with the norms or with the counter norms? And here you see a really big difference, right? So this actually is similar to my research on self and other knowledge and the accuracy of people's self-views. I don't know which of these is most accurate, but already there's some reason for concern about whether we're living up to these norms. So now I'm going to switch gears a little bit and talk about, okay, well, how can we do self-correction better in science? And I'm going to speak a lot about my home field of psychology, but I think a lot of this applies to many other fields. So I hope it won't seem too psychology specific. So in psychology, once we realized, okay, we have a problem, we started talking about, okay, how can we figure out which of our findings we can trust, and how can we correct the ones that are wrong? And one of the main approaches we've taken in our field so far are large-scale replication projects. So teams getting together, and what I mean by replication is actually running the study again, collecting new data, analyzing the new data, and seeing if the new study, the replication study, comports with the findings of the original study. So one of the most famous of these replication projects, and one of the earliest, was published in 2015. It was called the Replicability Project in Psychology, RPP. It was published in Science by the Open Science Collaboration, over 200 authors. So what they did was they took 100 original studies published in the top journals in psychology, and 97% of those had a significant key result. So in psychology, we use null hypothesis significance testing. We use a p-value of 0.05 as a threshold for statistical significance. And 97% of the original studies they sampled for replication found a significant finding. This is consistent with a lot of other literature showing that in psychology, over 90% of published findings report a significant result. It's similar in other fields, but psychology is a little bit more extreme. So then they ran replication studies. They tried to stick to the original methods and procedures as much as possible, adapt them when the original methods no longer make sense, like referring to a president that's no longer president or something like that. They tried to increase the sample size, so collect more observations in the replication studies than the original. And then they analyzed those data, and only 37% of them successfully replicated. This is a distribution of p-values in the replication studies. The effect sizes were much smaller. They didn't just stick to statistical significance in their analysis of the replication studies. There are different ways to look at whether the replication study succeeded or failed. But basically, a good estimate is that probably no more than 45% of the replication studies were successful. Since then, there have been a number of other large-scale replication projects across mostly the social sciences. So the one I just presented was the RPP in psychology. Here I'm going to call it 39 out of 100 successfully replicated. I'm using a slightly different criterion than p less than 0.05. Then there was one in econ where they attempted to replicate 18 studies and 11 were successful. And then there were 3 different projects called Many Labs in psychology, where they attempted to replicate a number of findings in the psychological literature with varying levels of success. And then most recently, a large team of researchers attempted to replicate every social science experiment published in Science or Nature between 2010 and 2015 that was easy enough to replicate, that didn't require really expensive equipment and so on. And they were successful for 13 out of 21 of those studies. So most of these studies were selected for replication because they were published in high-profile journals, had been cited a lot, were important theoretically, or foundational to the field. So this represents a particular selection of target studies to attempt to replicate, and not a random sample. So we have to be careful generalizing from this sample to any broader population, but it's still a data point about how many false positives are there out there and how many need to be corrected. So here, if we take the total number of successful applications out of attempts, it's 46%, which would mean something like a 54% false discovery rate in the literature. Something like half of published studies in the top journals, at least in psychology, may be generalizable to other social sciences. When we give it a good faith effort to replicate, many of these replications had much larger samples, much more rigorous methods, pre-registered, checking with the original authors to make sure the materials and methods are solid, and still about half only could be replicated successfully. So this tells us that there is a need for self-correction, right? There's false positives out there. Maybe it's not 50%, maybe it's lower, maybe it's higher. These are the top articles in the top journals in our field, so maybe the problem is actually even bigger than this. It might be smaller, it might be bigger, but it's certainly a problem. There's certainly things out there that need to be corrected. So I'm saying this is the hard way of doing self-correction because these projects are incredibly resource and time consuming, very, very difficult to do, and also probably not completely necessary. So one interesting finding from some of these replication projects is they paired the replication project with a prediction market where they asked participants who were mostly social scientists themselves to read just a short description of the study and then predict whether or not it would successfully replicate. And every time they've tried this, the prediction market has worked quite well. It's not that hard to predict which studies will successfully replicate and which ones are less likely to replicate. And this was captured in a tweet by my friend and podcast co-host Sanjay Srivastava. And the context for this tweet is this was after one of these large-scale replications with many, many researchers joining together to try to replicate a classic study in psychology. This classic study was published in the 80s, a long time ago. It had a very small sample size, ridiculously large effect size. If you're familiar with Cohen's d, the Cohen's d in this study was 5. Not 0.5, but 5. So they were claiming the two groups were 5 standard deviations apart from each other. And it was just an implausible effect when you look at it. So Sanjay tweeted, "This is no shade at the replication researchers, but science is self-correcting will be an empty slogan if we cannot collectively get past the place where it takes 22 labs and more than 7,000 subjects to counter a study that nobody should have believed in the first place." Right? So replication studies are a really rigorous way to try to self-correct, right? Saying we're going to do the whole study over again with a larger sample. We're going to pre-register. We're going to try to do everything we can to get the methods as close as possible to the original. And we can self-correct that way, right? We can find out with quite a bit of certainty which findings are more likely to be true positives, which findings are more likely to be false positives. But I would argue that there are probably too many false positive results out there for replication to be an efficient way to correct them all. Right? Running a new study is a lot of work, and if we need to throw everything into question and replicate everything before we know what's real and what's not, that's going to take forever. Another source of evidence that there are a lot of false positives out there. So one is the results of these replication studies, finding that a lot of the findings are hard to replicate. Another is a new source of information on the potential rate of false positives, which comes from comparing the traditional literature. So the traditional literature is where authors submit papers after they've run the studies, journals decide whether or not to publish them, and we see that something like 90% of published papers find a significant finding. But we know that there's bias coming in, both in terms of what authors choose to submit for publication, they're more likely to choose to submit significant results than null results, and what journals choose to publish. We know that journals are biased against publishing null results. So what we end up seeing is this first bar. This is from I didn't do this research, this is other authors' research, showing that the published literature, the traditional literature, the top bar, something like 95% or 80 to 95% of published findings are significant. It varies a little bit by field. Psychology is more towards the 95% end. And we can compare that to a small but growing literature of what's called registered reports that removes this bias. So the way registered reports works is authors submit their paper before they collect the data. So they describe the rationale for the study, the proposed methods, proposed analysis plan, and what conclusions they plan to draw, depending on how the results turn out. The journal sends that out for peer review. If the editor, after review, decides that this is an important study, well-designed, and they want to publish it regardless of the result, they give the paper an in-principle acceptance. And then as long as the authors do what they said they would do and that the quality checks for the data come out, the paper gets published regardless of whether it's a significant result or a null result. So we can look at the proportion of null results in registered reports. And there's over 100 registered reports in this sample. And they separated them by whether it's a novel study or replication study. But either way, we see a lot more null results in this set of studies than in the traditional literature. Now again, this isn't a representative sample of studies, right? People might choose particular studies for registered reports that are not representative of the broader population. So we have to take this with a grain of salt. But again, this is one more piece of evidence that a lot of these 80 to 95% of significant findings in this literature might actually be null results if we removed the bias that's selecting for significant studies. So if there's really 40, 50% false positives in some literatures, then doing replication projects is probably not going to be a realistic way to root all of those out and correct the literature. So I'm not the only one who thinks that there's a lot of replicability problems in literature. This was a survey done of mostly physical and natural scientists done by Nature. Again, not a representative sample, so take this with a grain of salt. But it suggests that there are quite a few scientists out there who agree that there's a reproducibility problem. I take that to mean that we're not as sure as we should be that the published findings that we're counting on are actually solid and we should be able to count on them. So I think there are probably too many false positives for replication to be a viable approach to self-correction in general. I think it's one tool, but we need other tools. Also, replication research is not valued. It's very hard to get a job for having done replication research. There's not a lot of rewards or incentives to do it. And then there's the fact that some studies can't be replicated in principle. So things that, studies that happened after an event that you can't just replicate that event, it may never happen again. Archaeology is a good example of where I think replication is quite difficult. So for all of these reasons, large-scale application projects are important, but I don't think they're enough to save us. I think we need to keep doing them. We need to invest in them. In psychology, they were critical for raising the alarm, right? For saying, hey, there might be something wrong here. You know, the first study, we tried to replicate 100 findings in our top journals, and we couldn't replicate more than half of them. That was really, really important for getting the field to pay attention and say, oh, wait, maybe there is a problem here. It wasn't without controversy. Not everybody agrees that it should be interpreted as a sign of a problem, but at least it raised awareness among some parts of the field. So what's happening is that we have published literature that looks quite different than the reality would look if we removed the bias. And we need to figure out a way to recover the more accurate picture of science from the too good to be true picture. We need to figure out how we get from there to here. So I'm going to argue today that we need to make self-correction easier. We need to make it so that it doesn't take these large replication projects to figure out what's likely to be true and what's likely to be a false positive. So there are two things we can do. We can produce fewer false findings in the first place, and we can make it easier to detect and correct false findings. So we're never going to get to 0% false positives. That shouldn't be the goal, right? You can't do science without making mistakes. We tolerate some amount of error when we do inferential statistics, but we can try to lower the error rates, and we can try to make it easier for others to detect and correct them. So this is what I think is the goal of what I've come to call the credibility revolution in psychology, and it's spreading to other fields. And the way I think about this is, again, I go back to what I teach my undergraduates. I teach them that scientists are supposed to prioritize self-correction. or in the words of a philosopher of science I met, we're supposed to be asking ourselves, how would I know if I was wrong? That's supposed to be at the forefront of our mind, right? And when I was thinking about this, I was in a meeting with some other scientists, and we were talking about transparency and reproducibility. And we were talking about, should it be the norm that people should have to share their data and their materials and be transparent and so on? And one scientist said, well, we can't demand that of people because that would be asking people to give their critics ammunition. And I thought, well, exactly. That's the answer to how would I know if I was wrong? I give my critics ammunition. I give people all the information they need to figure out if I'm wrong, and that will give me the best chance of getting caught if I am wrong, right? Of people correcting my errors. So I'm going to talk about 3.5 things that we can do to make self-correction easier. So the first is make correction easier by being transparent, which is really the main theme of this whole workshop, is how can we be more transparent? How can we do things in a more open way so that others can attempt to reproduce it? But I'm going to move on from that a little bit later on. But first, transparency. So some people argue that transparency just is what it is to do science, that there's no such thing as science without transparency. It is one of the defining characteristics of science. I find that argument quite compelling. It was expressed really well by Lupia and Ellman when they wrote, the credibility of scientific claims comes in part from the fact that their meaning is at a minimum available for other scholars to rigorously evaluate. Such open access to the origins of others' claims is the hallmark of scientific ways of knowing. So according to this view, it just is what it is to do science. You can't claim you're doing science if you don't let others verify your claims. This is also consistent with the motto of the oldest still existing society in science, the Royal Society of Science. Their motto is take no one's word. Or as I like to say, science means never having to say, trust me. Or I would tweak that a little bit and say science means never choosing to say, trust me. Sometimes we can't document things and let others verify them. There are things that aren't recordable. But whenever we have the choice, we should always choose to say, sure, go check for yourself, rather than no, take my word for it, trust me. So those are very lofty, moralistic arguments for transparency. I buy them. But for those who don't, there are also pragmatic arguments for transparency. So one of these I thought of when I read George Akerlof's paper. He was an economist. He wrote a paper called The Market for Lemons, Quality, Uncertainty, and the Market Mechanism. So I'm going to explain his argument real quick and then connect it back to transparency. His paper has nothing to do with transparency in science. In his paper, he used the used car market as an example of what happens when there's a lack of transparency. So in the used car market, at least historically, back in the 70s when he wrote this paper, sellers could hide a lot of information from buyers. They might know that a car, their engine is about to fail, or it's been in accidents, or things like that, and they didn't have to disclose that to buyers. So there was this information asymmetry between the sellers and the buyers knew that there was this information asymmetry, so that led to quality uncertainty on their part. They knew that they couldn't tell the quality of the different products apart, that a low-quality product looked just like a high-quality product, and that meant that sellers had an incentive to pass off a low-quality product as if it was high quality, and that they couldn't trust anything. And he showed mathematically that this leads to a vicious cycle, and people lose trust in the market and refuse to invest at all. And when I was reading this, I thought, this is a lot like how I feel when I'm reading a scientific paper. As an editor, as a reviewer, or just as a consumer of research, reading a published paper, I feel like I know that the authors know more than I know. Right? I know that they're allowed to leave out information. I know there's an information asymmetry between what the authors know and what I as the reader knows. And therefore, it's very hard for me to tell apart a high-quality product from a low-quality product. That leads to quality uncertainty on my part, and then eventually, if this keeps going, it leads to a vicious cycle where readers are going to refuse to invest in any of the findings or trust any of the findings. The kinds of information asymmetry I mean is the author might know that they tried several other studies that they didn't report, or measured several other variables that they didn't report, or ran several other analyses and cherry-picked the best-looking one. Right? I know that that's a norm in my field where that's permissible, and people do it, and so that leads to quality uncertainty on my part, and that threatens to erode trust in science. If readers start to come to realize that there's this information asymmetry, they will then no longer trust the findings in our published literature. A simpler way to say this is the way David Denoho said it in 1998. An article in a scientific publication is not the scholarship itself, it is merely advertising of the scholarship. So if we want people to trust us, we need to make sure that we reduce that information asymmetry between the authors and the readers, and that we give them the information they need so that they feel confident evaluating the quality of the products. They feel confident that they can tell apart high-quality products and low-quality products so that we don't lead to this vicious cycle. So what do I mean by transparency? What kind of information do readers need? This varies from field to field, but I think some things that generalize across a number of fields are transparency about what you did, so your materials, your procedures, any experimental scripts, or other kinds of descriptions of the methods. The data, whenever it's legally and ethically permissible to share the data should be shared along with the analysis code that's needed to reproduce the results in the paper. I think that'll be the focus of a lot of the material in this workshop. The third one is something I have mixed feelings about, but I'll leave it up here, disclosure of flexibility. So if you as the author know that you engaged in flexible research practice, you tried 10 different analyses or 10 different specifications for your analysis, and you have a favorite one, you should still disclose the other 9 that you tried. Now, as someone who studies self-knowledge, I'm very reluctant to rely on people's memory and disclosure about flexibility, because I think even when we're trying to be honest, we can easily mentally categorize another study as really it was about a different question. I don't need to report it because it's not exactly the same research question as this one. So it becomes very easy to kind of mentally separate the things that worked from things that didn't work and come up with good justifications for why you don't need to report the ones that didn't work. So I want to rely on self-report as little as possible. But if you do know and remember that you tried other things, you should report that. And then the fourth is something that goes by different names in different fields. In psychology, we call it pre-registration. In econ, they call it a pre-analysis plan. In clinical trials, it's a registry. But the idea here is that you write down what you're going to do ahead of time, and you let other people see your plan that was time-stamped and recorded ahead of time. This is important if you are asking your readers to trust that you plan things ahead of time, which matters for a lot of inferential statistics. So if you're using frequent test statistics, or in many cases Bayesian statistics, you are asking your readers to trust that your analysis that you're reporting was the analysis you planned to do before you saw your data. And if you're asking them to trust that, why not document it and let them verify that, right? If that wasn't the analysis you planned before you saw your data, then it changes the interpretation of the results. A p-value doesn't have the same meaning if the analysis was decided on after you saw the data. And the same is true in many other inferential statistics. So what does pre-registration look like? Well, so I'm going to skip this. Again, this is kind of psychology-specific language, but you can plug in whatever decisions you have to make in your field. So determine your methods ahead of time. In psychology, it might be your sample size, manipulations, measures, and your analytic strategy and how you're going to run the analysis. You can even write the analytic code before you collect your data. Write it down, and I would swap 3 and 4. You can collect data and then share your pre-registration. But the point is that you write it down and put it in a time-stamped place where it can't be changed. There's a lot of options for doing this. In psychology, most people use the open science framework, but there's other options. GitHub also allows you to do this. And you can keep it private if you want until you publish your claim and are asking people to believe your scientific claim. Then you should let them see this document and compare what you said you would do to what you actually did. So I put pre-registration under the umbrella of transparency because pre-registration is letting other people verify, so documenting and letting other people verify the timing of your decisions when the timing of your decisions matters, which it does for most inferential statistics. So if you're going to use statistics, it's a courtesy to your readers to let them check what you plan to do before you saw your data and how that changes, how you might have deviated from that plan after you saw your data. Okay, so that's kind of the number one goal of the credibility revolution, is to increase transparency so that we reduce this information asymmetry between authors and readers. People have more information. They can verify the validity of your claims. So transparency is really important. I think it's a necessary condition for credibility because it can allow for more correction, to detect errors, and so on. So if you're willing to give your critics ammunition and you and your findings stand up to that test, then that will increase your credibility. Or if you occasionally make errors, but not very often, right? Then that should increase your credibility. But transparency doesn't guarantee credibility. Transparency allows others to evaluate the credibility of your claims. It gives your critics ammunition. So transparency doesn't automatically lead to credibility. It leads to whatever you deserve, right? If you're transparent, one possibility is that people will find relatively few errors. They'll mostly say, yep, I did it again, you're right, that's what I found too. But another possibility is that if you're transparent, that'll lead your critics to have a lot of ammunition and make persistent and devastating criticisms of your work, and you will lose credibility, or we will lose credibility as a field. So there's no automatic goal. It doesn't necessarily go from transparency to credibility. It just goes to whatever we deserve, right? Transparency allows people to calibrate their confidence in our claims more appropriately. And what's the difference between these two possible outcomes? Strong methods. Right? If we're going to be more transparent, if we're going to give our critics ammunition, then it's all the more important that we do good research, right? That we make relatively few errors, that we don't give our critics too much ammunition. This was captured really well in a paper, a very short paper that I recommend by Andrew Gelman called Honesty and Transparency Are Not Enough. And in it, he wrote, consider the practical consequences for a researcher who eagerly accepts the message of ethical and practical values of sharing and openness, but does not learn about the importance of data quality. He or she could then just be driving very carefully and very efficiently into a brick wall, conducting transparent experiment after transparent experiment, and continuing to produce and publish noise. So transparency and openness are absolutely necessary for credible science, but they're not sufficient. And in fact, the more transparent and open we are, the more important it becomes to be doing solid science and using solid methods. So step one is to make correction easier by being transparent, but step two is make correction rare by using strong methods. And what this means varies by field, so I'll go through this pretty quickly because my slides are pretty psychology specific, but I hope that this will be translatable to your fields. So for one thing is everything we're already teaching in research methods, we need to keep in mind, right? And the more open and transparent we become, the more important those lessons become. So for me in the social sciences, it's things like construct validity. Are you operationalizing your constructs in a justifiable way? Internal validity. If you're making causal claims, does your design allow you to make causal claims? External validity and generalizability, and so on. One thing in my field that we realized we were especially getting wrong is that we were collecting way too few observations to detect the kinds of effects that we wanted to detect. So in psychology, we were often running studies with 50 or 100 people. And we thought that was enough to detect our effects because we were unknowingly engaging in flexible research practices like p-hacking, et cetera. And when we realized that we need to cut out those practices and do things more by the book, we realized that we actually need many more observations to detect the effects we're looking for. So we were running studies with too little precision or too little statistical power in the null hypothesis inference testing framework. So one important way that we in psychology need to improve our methods is to collect more observations, increase our sample sizes in many areas of psychology. But whatever the equivalent is in your field, the goal is to have more precise estimates, right? To reduce uncertainty, reduce sampling error. Another thing we should do before making strong claims, use all these strong methods, but also replicate our own work whenever possible. Now, this isn't always possible. Sometimes if you do, for example, longitudinal research in the social sciences, it might take decades to collect your data. You can't just run a replication study very easily. But when it is possible, try to internally replicate your own work, but to make sure you can consistently get the effect. And don't just run any studies and replicate them, but try to think of what are the studies that your critics would want you to run, what some philosophers of science call severe testing. So think about what would be something that someone who doesn't believe your effect would want to see in order to be convinced, and try to run those studies. Ask yourself what your critics would do, or even better, find some critics and try to do an adversarial collaboration with them. Try to design a test together that you all agree is a good test of the effect, and if it comes out one way, it'll convince one side, and if it comes out the other way, it'll convince the other side. So these are the kinds of things we should do before making strong claims so that we don't open ourselves up to a lot of criticism from our critics. So one thing we've learned in as a result of the replicability crisis in psychology that is applicable to other people who use p-values and significance testing, and I apologize if this doesn't apply to your field, the next couple minutes will be irrelevant to you, but this is a really neat tool and way to assess your own findings so that you don't let yourself fall into the trap of motivated reasoning and confirmation bias and believing something's there when it's really not there. And this is the idea of the p-curve, or the p-value distribution. So as it turns out, if you're studying something real, if there really is an effect, the null is false, there is an association between your variables, or there is a difference between the groups, then most studies should produce significant findings, assuming you have a decent sample size, you have decent statistical power. But moreover, the distribution of p-values p-values for those significant findings should be heavily right-skewed. Most p-values should be very close to 0, and few of them should be close to 0.05 or whatever your threshold is for significance, 0.10, some fields use that. And this was not intuitive to me, but it's actually a really useful tool because it helps us look at a pattern of results and say, does this look like the pattern of results we would expect if there really is an effect? There's a Shiny app that allows you to play around with what this distribution of p-values looks like at different levels of power. So this is, I asked it to return the p-curve for when you have 80% power, so you can change the effect size and the sample size to get different levels of power. So I set it to 80% power, and you can see so the x-axis is p-values from 0 to 1. The dotted red line is where p is 0.05. This is a threshold in my field. This is just a density plot. So you can see the distribution of p-values is heavily, heavily right-skewed. Most of them are very close to 0. And on this app, you can also pick a particular range and ask it to return the proportion of p-values in that range. So I asked it to return the proportion of p-values between 0.01 and 0.05. And it's telling me 20% of my p-values should be in that selection. So this is when there's a real effect and I have 80% power. So if I have 80% power, I know 80% of my p-values will be significant, 20% will be non-significant, false negative results. And only 20% will be between 0.01 and 0.05. So that means for every p-value I get between 0.01 and 0.05, I should get 3 that are less than 0.01. There should be a 3-to-1 ratio of p-values less than 0.01 to 0.01 to 0.05. This ratio is a little more even at lower levels of power, but it never goes much beyond 50-50. So even at the worst levels of power, for every p-value between 0.01 and 0.05 that you should get one below 0.01. So if you're consistently seeing p-values between 0.01 and 0.05, it's not coming from this distribution. Something else is going on. So if you want to really hold yourself to a high standard, you can run your study multiple times and not just make sure that you're getting significant results most of the time, but check to see that your p-curve is heavily right-skewed, that you're not just getting below 0.05 most of the time, but getting quite small p-values most of the time. And if you're not, then probably there's some flexibility getting introduced in there. When people unintentionally p-hack or engage in other questionable research practices, it changes the skew of the p-curve to become a little bit flatter. It leads to more p-values just below the 0.05 threshold. So you can check yourself and make sure that your set of results is realistic and is consistent with what you would get under this distribution. Or, as I called it in a blog post, you can be your own a-hole. So don't wait for a review or two to point out that your results are unrealistic. Check it for yourself. And in this blog post, I calculated the probability of getting, for example, 2 results between 0.01 and 0.05. At 80% power, it's only 4.4%. So if you do 2 studies and both of them end up with p-values between 0.01 and 0.05, you should be asking yourself, did I accidentally p-hack or somehow introduce some flexibility? At 3 studies, and they're all between 0.01 and 0.05, we're down to less than 1%. 4 studies, it's quite unlikely, right? So if you're reading a paper that uses p-values and that has a series of 4 or 5 studies and none of them get below 0.01, that's weird, right? That's not what happens when there's a real effect. Okay, so make correction rare by using strong methods and hold yourself to a high standard. So be your own reviewer too. Check yourself before you make a strong claim out there, before you give your critics ammunition. Make sure that you're being as hard on yourself as your critics are likely to be. Now, what if you can't reach those high standards? What if you can't run 4 or 5 replications or have a large sample size or have good internal validity, right? Sometimes we're studying messy things and it's hard to do all those things or impossible in some cases. So in those cases, we should calibrate our claims, right? If you know that your design doesn't allow for causal claims, don't make causal claims. Put that in a clearly marked speculation section in your discussion and really try to stop others from interpreting your results as supporting a causal claim. Or if you know that you have a lot of uncertainty around your result, that you couldn't get precision, you couldn't get the best methods, then make sure you write up your results that way so that when you're giving your critics ammunition and they come at you, you can say, yes, I agree. In fact, I said that in my paper. I said that we can't draw that conclusion. So I'm a fan of messy research. It doesn't all have to be perfect. If we required all research to be pre-registered and replicated and blah, 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 then we would only study really boring phenomena that are easy to isolate in the lab and control. I want to study the messy stuff too, but then we need to make sure we're calibrating our claims and only asking people to believe things that we can actually substantiate and justify. So I'm a personality psychologist. One of my favorite personality questionnaires, the first item on that questionnaire asks people whether this describes them or not, and the item is critical, skeptical, not easily impressed. And I think this is the attitude that scientists should have, including to their own findings, right? We should be critical, skeptical, and not easily impressed by our own findings. So this is what I mean by calibrating our claims. Think about what a critic would say and try to be your own critic. Okay, so the summary of what I think the credibility revolution is about, and sorry I'm over time so I'll go real quickly, is first transparency, and that's what we'll learn about today. But remember that when you're being transparent, you're opening yourself up to criticism, which is good. That's how we increase self-correction. But it means you need strong methods, and when you can't achieve the ideal methods, which most of the time we can't, we need calibrated claims. So I use the metaphor of safer science, just like safer sex. If you're going to do science, you're taking risks, right? There's no such thing as safe science. We're always going to make some mistakes. That's okay. And if we're transparent, people will catch our mistakes. So transparency is risky. So we should be transparent, but we should use protection. And that protection is strong methods, and when we can't achieve the perfect methods, calibrated claims. So I'm going to add one more addendum, because in my field, we've been working a lot towards these things, and there are more and more people doing replications, but also being transparent and writing criticisms of others' work and so on. And one of the things we're seeing is a lot of reaction and hostility towards the people doing the correction and criticism and so on. So I'm going to add a fourth step, which is love your critics. Try to create an incentive structure in your field where the people who are pointing out others' flaws, who are downloading their data, running their code, and saying, hey, this doesn't work, or I got a different answer, those people are the reason we can stand up and tell the public, hey, we believe in self-correction, we prioritize self-correction. So we need to value and incentivize that kind of work. We need to give those people jobs, we need to give them grants, and at the very least, not smear them and say that they're bullies or somehow a bad part of the field. They are the reason that we can call ourselves scientists and say that science is different from other ways of knowing, because we prioritize self-correction. So that's it. Thank you.
Great, thanks very much. That was really